Okay, so last time we introduced the vectors. Okay, let me check with you. What are the vectors? Amy.
They're like quantities with direction. Well, that's like the other meaning, but like it's like on a coordinate plane, it's basically an
Mm-hmm.
arrow. Yeah. Represented with an arrow.
With the direction and with the magnitude. Direction tells us where it goes, and the magnitude tells how far we go in that direction.
Question.
Yes.
But are vectors gonna be involved in algebra? I'm curious.
Yes, but it's closely related.
Aha, good.
Uh, so it will be if we have starting point, ending point, we normally use this P, Q for vectors. So from P to Q. We also use a lowercase letter for vectors. In our coordinate plane, we have the coordinates. If P has the point as coordinates A and B, Q with coordinates C and D, then the vector also has a coordinate representation. We use this bracket. Vector is a displacement from P to Q. The first coordinate tells us how much the first variable changed. So it will be C minus D. Second coordinate, how much the second coordinate changed from B to D, so D minus B. Okay. Now let me check with you. What are the coordinates of the following point, QP? Enter your answer in the chat. What's the difference between these two vectors? Amy, any thoughts?
Um,
How do you find? Uh-huh.
so it should be in like the reverse direction.
Okay, let me check. Uh, I made a
Maybe.
mistake in the previous one. I just realized C minus A or C minus D. That's a mistake. Let me
Okay, yeah,
correct
yeah,
it.
yeah.
Mhm. Make a correction. C minus A. Okay, Amy, your turn.
So I think it's A minus C and B minus D.
Okay, yes. When we compare these two vectors, this one from P to Q, we go this way. From Q to P, we go that way. We move to Q, we come back. A round trip, something like that. Okay. A special class of vectors is where we start from the origin, called position vectors. So for any point, we consider the vector from the origin. We call this the origin. Okay, what are the coordinates of this vector? Samuel, let's turn on the camera, Samuel. Okay. Samuel, any idea? How do we find the coordinates of this vector? The displacement. The coordinate will be the difference. Aaron, any guesses? Okay, Amy, you are fine.
0 minus A and 0 minus B.
Okay, so where do we start?
From
From O to P.
yeah.
So from P to Q, C minus A. So the target source.
Oh, okay. A minus 0 and B minus 0.
Yes, it's just A, B.
Wait, yeah, oh yeah. That's what I was
Okay,
gonna say.
now let's see the difference of these two. This one is a point. Each point, we have the x coordinate, y coordinate. We know where this point is. This one is a vector. I mean, the displacement from the origin to the point. You can draw a picture over there. Now we can see for any point on the plane, we have a vector from the origin, because the position vector. It tells us where this point is. If we move from the origin in that direction, this distance will arrive at P. Okay. The actually, how do we add two vectors? Vector addition. Given two vectors, okay, how do we add them? B, W. Okay, any guesses? Aaron, guesses? How do we add two vectors?
The triangle method.
Okay, we can use the triangle method.
We can draw the W from the V.
We can draw another vector, a copy of W at the endpoint of V. Let me draw a copy of this. And we use a different color to indicate this is a copy. These two vectors even though they are at different locations, they have the same direction, same size. So these two vectors are the same, even though they are at different places. Then the sum. Okay, so this is called the triangle method. There is another method. Amy, what would you do? Do you have a second approach?
You can do the uh
It's
I'm not really sure.
okay. It's
Uh,
the
I
parallelogram method.
oh, that's what I was gonna say.
Okay. This time we move. Okay. For easy drawing, I'm going to move this vector over to here. I'm going to draw a copy of V. If we put the V over here, that's the triangle method. We put the V at the same starting point. This will be parallelogram method. Okay, I make a copy of V. Then I draw the parallelogram. Okay, and we can check these two. Okay, my W is slightly shorter than I have over there. Let me make changes. Okay, so two different approaches to add a vector. Then how do we do vector subtraction? How do we subtract two vectors? Okay, Amy, what would you do? How do we subtract, have two vectors V and W? How do we define V subtract W?
Um, I think you have to like uh line like the points like the tail points
Ah,
up, I think.
okay, okay. So to define this, the first step, I want to convert this to a vector addition. What I should put over there? I will put the opposite
Oh, I'm
of
muted.
W.
Yeah, yeah.
Uh-huh.
I was
Okay.
muted, but that's what I
Okay.
said.
Okay. So we have two vectors, V and W. Let me make a copy of V. Negative W is the opposite of W. Oh, I said V, but I wrote W. V. Now we do vector addition. At addition, we use the parallelogram method.
Question.
Yes,
Will the triangle method work with this one?
they both works.
Aha.
So this will be V plus. Okay, so I tried this parallelogram method. You can try the triangle method. Now let's write it down the coordinate form. The coordinate form. So vector addition. Okay, I use 1 and 2 to indicate the first and the second coordinate of the vector. W1 and W2. First and second coordinates. Then the vector addition. There will be the summation of the two coordinates. V1, W1, V2, W2. Okay, Aaron, the formula for the subtraction.
Hold on.
Mm-hmm.
Basically V1 minus W1 and then V2 minus W2.
Be the difference of the coordinate. Okay, either form. Then we introduce another one, the scalar product. So give it now a number. It's called a scalar. No direction, only magnitude. Only magnitude. Not good. Let's forget about this. It's just a number. The V a vector can define a new vector be the multiplication of each coordinate. So it's a multiplication or the product of a scalar with a vector. Why do we call it scalar product? Well, why don't we not just call it a product? We put a scalar over there because we want to introduce more and different products between vectors and numbers. Before we move on, let's have some practice. Suppose V equals 1, 2. One, 3. A equals 2. Okay. Let's find A, B. Coordinates of the scalar product, then vector addition. Enter your answer in the chat. Scalar product A, V, B, W. Uh-huh. Okay, have one answer over there. Amy is still entering.
I'm confused. How did Aaron get -10 and -5?
They're
Uh,
numbers.
Okay, step by step. Amy, what's A times V?
A times V is 2.
Okay, let's check. A is
Well, the first,
2,
yeah.
V is 1, 2.
So 2 and 4.
Okay, so the first part will be 2 and
Oh,
4.
oh, 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 oh. I'm sorry. I missed the B. I thought the B was a 3, not a -3.
Okay, okay. 2 and 4 plus. Okay, Amy, you checked it as what's BW?
That's -12 and -9.
Okay, nice. Then we add them. We get okay. So the scalar multiplication and vector addition.
Wait, so I'm just trying to clarify here. You add them, right? Oh, someone's texting me.
So first scalar product, second scalar product. Then I add them. 2 add -12, -10. 4 and -9, -5. Okay, so I add them. Okay. Now a new operation. It's called the dot product. Very important one.
Isn't that like when you multiply them together?
Kind of dot product.
Wait, absolute value?
So given two vectors, v, okay, two coordinates, v1, v2, w, w1, w2. We define a new product, vector v and w. So here I emphasize we have a dot over there, this the dot product is defined as the product of the first component, v1, w1, the product of the second component, v2, w2. Then we add them. So this is called the dot product. So you see the difference between these two products. For this one, the input have a scalar and a vector. The output, a new vector. The dot product, the input are two vectors, v and w. The output, okay, let me check with Aaron. This a number or a vector?
I believe that it can represent number.
Okay, yes. So the dot product of two vectors give us a number. It's very important. So this is a number. A very common mistake is this. Okay, now we can see the difference of these two. This one is a number. This one is a vector. But this is not what the dot product does. So I will put a sum there. That's incorrect. This is the common mistake. Whenever we do dot product, we expect a number. Okay, let's check. We have two vectors over there. Let's find their dot product. One, two, four, three. Let's find v dot w. W dot v.
Uh, Wait, oh.
Mm-hmm. Amy, where do we start?
You want to do V1 W1 plus V2 W2.
I think that's 10, to be honest.
Mm-hmm.
Yeah.
Going to be 1, 4, 2, 3. Wrong order. Okay, Aaron, second one. W dot V.
That's W1 times V1, which is 4 times 1, I think. And
Mm-hmm.
and then it's still 3 times 2, still be 10. They're the same thing, I believe.
Okay. Now we can see we have the commutative rule for dot product. Okay. The dot product of V with W, the same as W with V. Okay, could we find the dot product of a vector with itself? So V is, okay, A and B. What's V dot V? Okay, tell me your answers.
I think that's A squared plus B squared.
Okay, so it will be V is AB dot AB. The product of the first coordinates will be A squared. Product of second coordinate of B squared. Now we can see this. If we take a square root, they give us we call this square root. We call it the norm. How large the vector is. Okay. In particular, we have the following formula. Norm square is always a very useful formula. We will use this repeatedly in the following theorems. Whenever we see square of the norm, we can replace it by the dot product of vector with itself. Okay, these two vectors, let's find their norm. Find their norm. Samuel, do you know how to find the norm of a vector? No. Okay.
Wait,
Given a vector
I think I might know.
with, okay, Aaron, how do you find this?
This is a bold take, but I think normal v I think is root 5.
How did you get this?
It's like it's basically just 1 squared plus 2 squared, which is 1 plus 4, and then that's just root 5.
Okay, Samuel. So the norm of a vector is the square of the sum of the squares of the two coordinates. 1 square, 2 square, take square root. Okay, Samuel, let's find the norm of W.
So that's just square root over 4 to the power of 2 plus 3 to the power of 2.
Okay, 3.
Only
That's
5? That's 5.
okay, so now we have the norm of W. Okay.
Alright.
Aaron, stop entering this. I'm going to disable this.
Hmm? Hmm?
Okay.
I don't know how that happened.
Okay.
I
Okay.
pressed Control V, I guess. I guess I pressed Control V.
Okay. Uh, so we have the commutative rule. Next, we have the distributive rule. Uh, there are two forms. One is about the scalar product. We distribute the scalar to both V and W. And we have one for the dot product. Again, we distribute U to both V and W. Okay. Both of this follow the same rule for numbers, and you can verify this using the coordinates. I will let you check this after class. Okay. Next, now we are ready to give you a very important theorem about the dot product. I will start with a formula, a graph. Let's put two vectors over there. One vector V, one vector W. I'll make it this way. Given two vectors, we can measure the angle between them. This angle is closely related to our dot product. Okay. The dot product is almost, okay, I will leave something to be complete later, but first let's check. This is a number. It's the norm of the vector, another number. So the dot product is a number. The difference between the dot product and the product of the norms is calculated by the angle. This kind of the
Wait,
geometry. Yes.
what would be cosine of that angle?
Okay, so now we have two applications. If we know the coordinates, we can find the dot product, the norm, then we can find the cosine.
Okay.
So we get some knowledge about the angle. Another way, if we know the angle, we know the norm, then we can compute the dot product. Okay, so two applications. Okay, it depends on what we know. If we know the dot product, then we can find angle. if we know something about the angle, we can go back to find the dot product. We will prove this after the break, but let's first have some examples. And this is example 4. Consider the following vector. E 1, 2, W. Let's find their dot product. And let's guess what their cosine, the angle between them is. Theta, the angle. Okay, let's find the dot product first. What do you get?
Okay, I got -2 plus 2, which is 0.
Okay, so we have 1, 2, 2 times 1. Okay, so the dot product is 0. Amy, what's the cosine theta?
Um, uh,
Okay, let's go back to there. In this formula, this is 0. What can I say about this?
That could be 0.
Could be or must be.
uh, probably must be.
Okay, so because the norm not a 0, norm not a 0, both
Well,
are not a 0 vector. So the product is 0. This must be 0. Okay. This is dot product, norm product. Okay, now let's refresh our memory. Which angle has cosine 0?
I should remember this.
I believe it would be 0.
1.
Okay. Think about it. We will continue from there
Oh wait,
after the
no,
break.
I don't know.
Okay, after the break. After the
There's two
break.
possible choices.
Okay. So we'll be back at 8:20.
Okay. Okay, bye.
Mm. Okay, time to get back. Fred, Samuel, Aaron, Amy here, Sophie, and Peter. Okay, now let's check. What's this angle theta? Amy, what's your guess? What's your answer?
Um,
Cosine is 0.
Oh, I think I know.
Okay, Aaron.
Both take, but pi over 2.
Okay, so that will be pi over
oh
2.
wait. Yeah, I think so. I agree with him. Yeah.
Okay. Angle is pi over 2. What does this mean?
Then that means, how do I say it again?
They are perpendicular or orthogonal.
I think so, yeah. Because
This means,
that's 90 degrees.
yes, the two vectors.
Well, there's also one other possibility. If there's a 360 degrees involved, I think.
Okay.
Is it 3 pi over 2?
That also works, yes.
Okay.
So when we see the, okay, Aaron, the angle between two vectors, could this be 3 pi over 2?
Well, from the looks of it, it doesn't look perpendicular, so
Okay. So given two vectors, we normally pick this angle. The smaller angle to be the angle between two vectors. We do not pick this one.
uh-huh.
Okay, so we pick the smaller one because it's angle between two vectors.
Mm-hmm.
Okay, so I will use a notation that they are perpendicular. V perpendicular. Okay, so two vectors are perpendicular. Then we have the following. So this is our observation. If the dot product is 0, then they must be perpendicular. If we know the dot product is 0, then it's perpendicular. The other way, if we know two vectors are perpendicular, their dot product must be 0. That goes both ways. So this is a special case of the application we mentioned over there. We can use dot product to find cosine theta. We can even find theta. We use the angle to find the dot product. Dot product, angle, dot product. Okay, very useful formula. But why? How to prove this? Okay, now we will prove. To prove this, just recall the law of cosine. What does that tell us? Okay, so we start with two vectors. Call this V. We call this W. This is the theta. I'm going to connect these 2 points. Now we have a triangle. I'm going to label this C, A, B. I put the starting points of the two vectors at a common point. I could label this C. First vector end at A, second vector end at B. So we have a triangle ABC. For this triangle ABC, law of cosine. Okay, let's give you a few minutes to recall. What's the law of cosine?
I think it's A over cosine A equals B
That's
over
law of science.
Okay, right.
Uh,
Okay, I'm getting them confused.
Uh-huh.
It's the
like
other one, yeah.
Okay,
cosine.
Aaron.
I mean, cosine A over angle A over A or something like that equals cosine angle B over B. And that's
No, we don't have this.
That's
We only have a law of sine. We don't have this. Law of cosine is different.
wait, let me check. Let me check.
Okay, so I'm going to write down the formula. There are different ways to say this. AB squared equals AC squared, BC squared. If this is a right angle, then this will have this identity. For general angle, we have the correction term.
It's a B? Okay, yeah.
In our previous lecture, we call this side C. We call this side A, this side B. So this is C squared equals B squared BC, A squared. Okay, law of cosine. Okay, so in this setting, this is side, the length of the side is also the norm of the vector. AC. So B is the norm of the vector. A is the norm W. Okay, what about C?
C's
Norm of something.
mhm. Uh wait, what was B again? Root 5? That.
No, this is a general setting.
Oh, sorry.
A
No.
general vector. General vector. Okay. So is it V plus W? No. Okay, Amy said no. Why?
Wait, never mind. Wait.
Okay.
I need to rethink my life choices. Um,
Uh-huh.
yeah, I think it is.
Yes or no? Uh-huh.
Yes.
Okay. So now let's check. We have vector v, vector w. How do we add them? We move this to the endpoint, then we connect. This is summation.
Oh,
It's
okay.
different from this. What's this?
That is the opposite of that. Yeah.
Okay. Oh, yes. So this will be the difference, not the summation. So we can see if we start with v, we add this vector, we get w. So w is the sum of these two. W. So if v plus ab equals w, this implies ab is, in particular, c is the norm. Okay, it's not a sum, but it's close. It's the difference. Because if we start with v, we add this, we get a w. So w minus v is this side. Okay, now we are going to put everything back to the equation. We start with c squared. C squared.
That the norm squared, W minus V squared, something like that.
Okay, w minus v norm square.
Uh-huh.
How do we simplify norm square?
That's just basically no norm anymore, I think.
So if we go back to the previous page, norm square is the dot product of the vector with itself.
Mm-hmm.
Okay, we're going to apply this to our expression here.
But that's a plus, I think. Oh, minus, yeah. Well, soon.
So this,
Oh,
the
是我得
whole
懂
thing,
了。
okay, okay. The whole thing will be our vector. It's the dot product of the vector with itself. Okay. Next, I'm going to apply the distributive rule. Dot product of a vector to the summation and distribute, the same thing applies. We will apply the distributive rule to this too.
So it's basically just quadratics, but with vectors.
With vectors, yes.
It's
If it's just
very
numbers, have the quadratic formula. But for vectors, you be very careful. We have to use this dot product. Amy, that's what you want to say? Okay, so let's continue from there. I copy the first vector. I distributed it to the difference. I keep the dot product. Next, I'm going to apply the distributive rule again. This time, I distributed W to both of them.
I think that's
V, yes, Aaron,
I think it's W squared, I think, if that's the correct notation, minus 2VW.
will be there.
Uh-huh.
For this one, minus sign, distribute V to W. Oh, mistake, should be V. Distribute V to V.
Uh-huh.
Okay, now let's see. A vector dot product with itself. What's this?
Which one? Uh,
We will apply the same formula. The dot product of a vector with itself. And you see, where is it? The dot product of a vector with itself is the square of the norm.
mm-hmm.
Okay, it's the square of the norm. Okay. For this one, I will just copy it, distribute the negative sign. Distribute negative sign. Okay, Amy, the dot product of a vector with itself. How do you simplify this?
That would be the absolute value of.
Okay, we call it a norm. Okay.
Okay.
Yeah. If it's a real number, we call it absolute value. If it's a complex number, we call it the norm. So here it's also the norm. Okay, now let's check what is norm of W. Okay, we have over there. Norm of W is this side A. Okay,
A squared.
A squared. As we mentioned before, the dot product is commutative. So VW, WV, they're the same. I'm going to write 2VW. Okay, last part, norm V squared. How do we simplify this?
B squared.
B squared, yes.
Hold on. Wait, so it's basically just to A squared minus 2AB plus B squared, I see now.
Yes. Now we are going to apply the other side of the law of cosine.
But
We
that's just,
started with C squared. This should be the same as this. Okay, I'm going to copy this to the end. Okay, so by law of cosine, this is A squared, B squared.
that is the same. Because cosine's 0, I think.
Law of cosine. Okay, now we simplify. A goes away, B goes away. Negative 2 goes away. Only this left. And we can switch back to, so A is W, B is V. This is V. I changed the order because just multiplication. Okay. This is what we want. The dot product of two vectors, a product of their norms and the cosine of the angle between them. We have this formula. Okay, let's recall the two vectors we had at the very beginning. 5 V is 1, 2. W is 4, 3. Let's find the cosine theta. Okay, I will give a few minutes to work on this. How do we find cosine theta? Okay, Amy and Aaron, what are your approaches?
Well, you could. Okay, wait, I'm a little confused, but you could graph it first, maybe. And
Okay, we could. Let me graph this. 1, 2, 1. Okay, wrong direction. X1, y equals to 2 over there. 4, 3. This is B. This is W. This. Okay, in this formula, oh, that's mm-hmm. This
well,
formula, could we find the norm of V?
yeah.
Okay, what's the norm of V?
1 squared plus 2 squared under a square root. So that's a square root of 5.
Uh,
What's the, okay, Aaron, norm of W?
yeah, that's 5.
5.
And
What's
then
the dot product? Uh-huh.
dot product, that's basically somewhere between, I mean 10, yes, 10. And then that
Okay, because, yes.
equals, let me think. Root 5, I mean 5 times root 5 times cos 0. So cosine 0 equals 10 over I mean 5 root 5.
So 10 is root 5, 5 cosine theta. From there, we conclude cosine theta is 10.
Over 5 root 5. And then that can be simplified to 2 over root 5.
So even though we don't know what this angle is, but we know the cosine of this is square root of 2 over square root of 5. Okay, let's try another one. Example 6. Given two vectors, we know that could you find the dot product based on the information we have over here?
We'd have to go backwards then.
Okay, where do we start?
So V times W would equal 3 times 4 times the theta.
So this is 3, this is 4, cosine pair with 3. What is cosine pair with 3?
I believe that's how much was that again?
Wait, I have a chart. Not to wait.
Oh yeah, that's 6. The entire thing is gonna be 6 because cosine pi over 3 is pi over 3 is 60 degrees, which equals 1/2.
Okay. So you can see, even though we have no idea what these two vectors are, still we can find the dot product. This is another application of this formula.
So
One
then,
way we can find the cosine theta, the other we can find the dot product. Yes, Aaron.
and then that just means uh v times w equals 6.
The dot product. So because now time has ambiguity, we don't know what the time is.
Oh, wait, yeah. Dot product equals 6.
Dot product. Okay. Next one. What's the caution? Given two numbers, let's say A, B equals 1. What can we say about A and B, the two numbers?
There's no reciprocal?
They're reciprocals. In particular, we can write B is 1 over A, the reciprocal. Now if you have two vectors,
I think they can be reciprocals if they're lines.
do we have a reciprocal of vectors?
No, lines can't be reciprocals.
Okay, so if W, I'm going to write something. This is incorrect. There's no reciprocal of vectors. Okay, for example, let's check. This will be 7. V equals 1, 2. W equals 4, 3. And U equals 2, 2. Two, 4. Let's check the dot product. VW, VU.
They're both 10.
Okay, they are both 10. Okay, so the same vector dot product with two different vectors gave us the same number. Even though it is not a zero, we cannot take the reciprocal because these two vectors are different. Yes, they were reciprocal. We would get something ridiculous. These two vectors are different, but they are both the reciprocal. So it doesn't work this way, a contradiction.
Wait, what do you mean by ridiculous?
So V and U, they are clearly different.
Aha.
If they were reciprocal of vectors, okay, maybe of vectors, then we will have something strange. The two different vectors turn out to be the same. So this is a mistake. We cannot have this. We cannot have reciprocal of vectors. There's no division. Unlike the numbers, if the number is not a zero, then divide by it. But the vectors, there's no such thing. Okay. Next, let's recall the first postulate of Euclidean geometry. What's the first postulate? Okay, you have 5 of them. Who remember this?
What's about lines?
Okay, given any 2 points,
There's a line between, there could be a line established.
we can so A, B. Well, I'm going to adjust it. I'm going to adjust it. Okay, so this is the first postulate. For any 2 points, connect them, we get a line. This is a geometric object. Now we put everything in coordinates. Geometry, coordinate. Okay, now we're going to draw a coordinate system. Okay, for this 2 points, we will have two coordinates. We call this A, the x coordinate, x A, y A. B, the coordinate, x B, y B. We want to describe this line through A and B. Okay, so the first observation we have, let's compare the different lines. This line with this line. Okay, how do we distinguish these three lines? An important feature is the slope, how steep the lines are. So we can see for this one, it's not that steep, to grow slowly. This goes faster, but this even faster. This is the geometric object slope of a line. We use m for the slope. It will be the difference, the quotient of the difference. The slope of this line is the quotient of difference of the y coordinate over the difference of the x coordinate. Okay, let's check.
You can just pull back up a little bit,
Uh-huh.
just a little bit. Okay, good.
Okay, so I'm going to write down our last example. This will be 8.
Wait, so this is algebra basically, because slope is like
Yes, it's closely related. The geometry and the algebra are kind of closely related.
it's like something about y equals mx over y equals mx plus b or something like that.
Yes.
And then m is the
So
slope.
1, 2, 3, 4, 3. Let's find the slope of the line through A and B.
Okay. The slope's like 3 or something. It's 3 over 1.
Okay, how do you get this?
Because it's 4 minus 1 over 3 minus 2, which is
Y, B, Y, A, X, B, X, A. Y, B is 3. Y, A is 2. X, B is 4. This is 1.
oh no
So
no no, sorry.
1.
I said in reverse, sorry.
Okay, okay. So it's the quotient of the difference of the y coordinate over the x coordinate. Okay, so this is the slope. Okay, so we will stop here and we will ask any questions.
Nah. Bye.
No? Okay.